Hello, and welcome to The Space Above Us, Episode 18, Project Gemini Flight 6, Gemini VIII, Neil and Dave's terrible, horrible, no good, very bad orbit. Here's something to think about. If Gemini VII had launched at the moment that the previous episode of this podcast went live, and if you are listening to this episode the moment it goes live, well, thanks for being such a dedicated listener. I hope you left an iTunes review, but that's beside the point. If those things were true, then Gemini 7 would have landed about 5.5 hours ago. When that thought struck me, it really drove home just how ridiculously long a mission Frank Borman and Jim Lovell had signed up for. Gemini 7 nearly doubled America's total time in space in one fell swoop, and its scientific contributions gave NASA confidence that remaining weightless during the long trip to the moon and back would pose no medical issues. The mission firmly checked the box next to one of Project Gemini's main goals, proving long-duration flight was possible. But there were other questions left to answer. Let's take a quick look back at Project Gemini so far and see what its goals were. Gemini 3 proved that the capsule would work as expected. Gemini 4 took the first steps towards orbital rendezvous with its failed attempt at station keeping, flew the longest yet mission at over 4 days, and performed the first American spacewalk. Gemini 5 took long duration even further and stayed aloft longer than a round trip to the moon and back would take. Gemini 6A performed the first successful orbital rendezvous using Gemini 7 as a target, and of course Gemini 7 made a mockery of all other long-duration flights. And what were the original goals? Well, learn how to stay in space for the extended durations required by a moon landing, up to 2 weeks. Check. Learn how to rendezvous and dock with another spacecraft in orbit. Half a check. Learn how to safely exit the spacecraft and perform useful operations in space. Again, half a check. Ed White had fun but didn't really do anything all that useful. And lastly, learn how to land more precisely than Project Mercury, ideally on land, to ease recovery operations. Let's call that half a check as well. But that's not bad. Other than landing on land, which went out the window along with the inflatable Rogallo wing, things seem to be going pretty well. There are really only 2 big things left to do: docking and useful work on an EVA. Enter Gemini 8. After a series of delays and its failed flight as part of Gemini 6, the Agena target vehicle was at last ready for its big moment. The goal of Gemini 8 would be to chase down the Agena, rendezvous with it, and dock with it, forming a solid connection with the other vehicle. While there, the pilot would perform the most complicated EVA yet. He would first set up a video camera and then retrieve a science experiment from the exterior of the Gemini capsule. Next, he would take advantage of a new lengthier tether to work his way over to the Agena spacecraft. While there, he would retrieve another science experiment related to micrometeoroids. After returning to the Gemini, he would then evaluate a specialized power tool designed to operate effectively in the weightless environment of space. He'd do this by loosening and tightening some bolts that didn't actually do anything, which I thought was pretty funny, but I guess being able to use power tools would be a pretty critical skill later in the space program, so they may as well start practicing. Lastly, he would don an experimental jetpack developed by the Air Force that was similar to the rocket-powered backpack you may be familiar with from famous photos taken in the shuttle era. He would then use the jetpack, known as the Extravehicular Support Pack, or ESP, as well as an improved version of Ed White's zip gun, to fly up to 100 feet away from the spacecraft. When he finally returned to the cabin, over 2 hours would have passed, meaning he would have flown completely around the world outside of the vehicle. To accomplish this first ever docking in space and such an ambitious EVA, NASA was going to need one heck of a crew. Serving as command pilot for Gemini 8 was Neil Armstrong. Neil Armstrong was born on August 5, 1930 in Wapakoneta, Ohio. Armstrong wanted to be a pilot ever since he was a child, and earned the right to fly solo before even attaining his driver's license. He attended Purdue University, studying aeronautical engineering. Armstrong's tuition was paid for by the Navy as part of the Halloway Plan. In exchange for his tuition, Armstrong committed to 2 years of college, 2 years of flight training, 1 year serving as a naval aviator, and then another 2 years of college to complete his degree. During his time as a naval aviator, he flew 78 missions in the Korean War, performing bombing runs, reconnaissance, and flying jet fighters. After his time in the Navy, he returned to school and completed his degree in aeronautical engineering. He next applied to NACA, the predecessor of NASA, to work as a test pilot. He started his career at the Lewis Flight Propulsion Laboratory in Ohio, before moving to the high-speed flight station at Edwards Air Force Base in California. While at Edwards, he flew a number of different experimental aircraft and eventually entered into our narrative as an X-15 pilot. He flew the experimental rocket plane 7 times, up to a peak altitude of 207,500 feet, and specialized in the control systems necessary for flight above the atmosphere. NASA was actually his third attempt to reach space. He was first selected as part of the Air Force's Man in Space Soonest project, which was abandoned in favor of Project Mercury when NASA was founded. He was next chosen as a pilot of the also canceled X-20, aka Dyna-Soar, short for Dynamic Soarer. He finally got his chance as part of the second astronaut group, the New Nine, in 1962. This was his first of 2 space flights, and I think you can guess the second one. David Scott, who would serve as pilot on Gemini VIII, was born on June 6, 1932, in San Antonio, Texas. Scott briefly attended the University of Michigan before leaving for West Point, where he finished near the top of his class. He next joined the U.S. Air Force in the hopes of becoming a jet pilot. His wish was granted, and he spent 4 years flying fighter jets over Europe as part of the 32nd Tactical Fighter Squadron based in the Netherlands. After that, he returned to the U.S. and attended MIT, where he received a master's degree in aeronautics and astronautics. He was chosen as part of the third astronaut group, the 14, and was the first from the group to fly in space. This was his first of 3 spaceflights. Now, we've already talked about rendezvous, in what some might call incomprehensible detail, in the episode on Gemini VIa, but we haven't quite gotten to docking yet. Docking is one of the many topics in spaceflight that I didn't really give much thought to because it seemed pretty straightforward. Get to the other spacecraft, the hard part, connect to it, and you're done. It turns out it's quite a bit more complicated than that. So let's start on the Gemini side. At the front of the Gemini spacecraft is a sort of truncated cone called the Rendezvous and Recovery section. The recovery part of the name comes from the drogue parachute and main parachute stuffed somewhere in there, but that doesn't come into this part of the story. The rendezvous part is what we want. First, there's the fairing. This is a protective cover that sits in front of the delicate instruments we're about to talk about and protects it during the punishing ride uphill at launch. Shortly after the spacecraft separates from the booster, the whole cover springs open on a hinge and flies off into space, never to be seen again. Beneath the fairing is the rendezvous radar and 3 latch receptacles, with the radar in the front and the receptacles spaced evenly around the sides. The rendezvous radar bounces radio waves off of the target vehicle and then detects the return signal to determine how far away it is and how rapidly the capsule is closing in on it. It also allowed the crew to send commands to the target vehicle. The latch receptacles are yet another one of these things that sounds simple until you dig into it. They provide a place for the docking cone latches to hook onto, but they can't be left open during re-entry or the hot gases would get in there. So, when the mission is over, the crew jettisons them and activates pyrotechnics that blast covers over the holes they left behind. Space is nuts, you guys. Lastly, to help make sure that the 2 vehicles are aligned properly, an indexing bar is extended from the rendezvous and recovery section to serve as a visual aid. Just imagine a metal pole a few feet long sticking straight up out of the front of the hood of a car, and you'll have a good idea of what the astronauts would see. On the Agena target vehicle side was the docking adapter. The most obvious part of this was a large cone that helped guide the R&R section of the Gemini spacecraft into place. I haven't been able to find what this cone is made of. I don't really need a reason, I just kind of want to know. So if someone out there actually knows, please shoot me an email. Sticking out of the cone, towards the direction the Gemini would approach from, were long, thin metal rods that would help prevent static electricity discharges that would disrupt the sensitive electronics. A large notch was cut out of the top of the cone so that the indexing bar could stick out and allow the command pilot to see if he was oriented correctly. Inside the cone were several latches that would grab onto the latch receptacles on the Gemini capsule. There were also electrical contacts that would touch pads on the Gemini, creating a hardwired electrical connection between the two vehicles. This ensured that the crew could send commands to the Agena. The entire cone was mounted on a series of linkages inside the docking adapter, which helped absorb the impact of the 8,000-pound capsule flying into it. Once the latches were secured, a motor would engage and retract the linkages, rigidizing the entire system. Without this last step, the shock-absorbing joint would be all floppy, and no one wants to fly a spaceship like that. The crew could check the status of all this by looking at a series of indicator lights mounted above the cone. The lights informed the crew of the status of the Agena propulsion systems, attitude control system, soft docking, and hard docking. All an astronaut needs. Alright, that's enough talking about docking. Let's go do it. You guys know how this works at this point. On March 16th, 1966, an Atlas booster rocketed off into the sky, carrying the Agena target vehicle. An hour and 41 minutes later, at 10:41 a.m., Neil Armstrong and David Scott bade farewell to Launch Complex 19 and began their hunt for the Agena. Ascent, spacecraft separation, and initial orbital corrections all went off without a hitch. The crew settled in for the chase and began to unpack some of the equipment they would use on the 3-day mission. They even took some time to eat a weightless meal consisting of chicken and gravy, apricot pudding, brownies, fruit drinks, and my favorite, bread cubes. Why the bread had to come in cube form, I am not sure. Flying the same type of co-elliptic rendezvous pattern as described in the episode on Gemini 6A, the crew of Gemini 8 continued to close in on their target. At a range of about 200 miles, their rendezvous radar locked onto the transponder in the Agena, providing them with range and rate data. Before long, the crew found themselves performing the final small braking maneuvers and easing up next to the Agena just 150 feet away. Rendezvous had been achieved, but could Armstrong pull off the docking? Armstrong fired his thrusters and slowly approached the target vehicle. He found that flying the capsule near the Agena posed no problems. He positioned the capsule a few feet from the docking cone and held it there until they passed over a telemetry ship several minutes later. Once the telemetry ship was in range, he scooted the spacecraft forward, the latches grabbed on, the drive system engaged, and Gemini 8 was hard docked to the Agena. Neil Armstrong had performed the first docking of 2 vehicles in orbit. He called down simply, "Flight, we are docked." With rendezvous and docking accomplished, Gemini 8 had already pulled off 2 of its major objectives. As the spacecraft flew into orbital night and out of range of radios on the ground, the crew could relax for a moment, knowing that the mission was going perfectly. But something unexpected happened in the Earth's shadow. David Scott noticed that the instruments indicated the capsule had yawed 30 degrees off track and was still going. With nothing but darkness visible outside the windows, except for the Agena docking cone, such a misalignment was an easy thing to overlook. Whatever was causing this attitude deviation was happening so gently that neither astronaut had felt the motion. Turning 30 degrees is no major emergency, but the rate of rotation was increasing. Armstrong took control and used the ohms thrusters to null the rates, NASA speak for stop the spinning. He was able to do so, but the spin just started back up again. Since they were out of range of ground stations, the crew were going to have to solve this problem themselves. They suspected something had gone awry with the attitude control system on the Agena and commanded it to shut down. For a few minutes, everything seemed to be under control, but the unexpected yaw and roll motion returned again. The crew decided that it was best to separate from the Agena while rotation rates were small so that they could undock safely and would then at least know if the problem was with the target spacecraft or their own. Armstrong slowed the spin down to an acceptable level and had the presence of mind to not only perform a normal undocking as opposed to an emergency one, which would make it impossible to try to dock again later in the mission, but to also transfer control of the Agena back to the ground. Gemini 8 separated cleanly from the Agena, but it quickly became apparent that the problem was with the Gemini spacecraft itself. The spacecraft began to spin faster and faster in an uncontrollable yaw and roll motion. Eventually, the spin increased to as fast as a full 360-degree rotation every second. This was so fast that the astronauts' vision was starting to blur, making it difficult to even read their instruments, let alone fix the problem. At this point, two catastrophic events were a very real possibility. First, the crew could lose consciousness as the rapid spin pulled the blood from their brains and caused them to black out. Unconscious astronauts are not the best problem solvers. Second, the spacecraft could actually spin so fast that it could tear itself apart. Space vehicles have to take a lot of stress in a lot of difficult situations, but they're designed to handle those very specific stresses in those very specific difficult situations, and not much else. Designing a Gemini capsule that could spin at ridiculous speeds without breaking apart would just be wasting weight. So let's see what we've got here. We've got two guys, a couple hundred miles up in space, with no radio contact with the ground, spinning so fast that their vision is blurring and they're about to black out. This seems like a good time to remind you all of how emergency deorbits work. No reason. As a spacecraft orbits in low Earth orbit, the Earth itself rotates underneath it. Every time it finishes one full revolution around the world, the path it traces on the ground moves several hundred miles to the west as the Earth rotates. After enough orbits, the spacecraft will pass over every point on Earth in a swath north and south of the equator defined by the orbit's tilt relative to the equator. To give you an idea of what I mean, if the orbit's inclination was 45 degrees, the spacecraft would eventually pass over every point on Earth between 45 degrees latitude north of the equator and 45 degrees latitude south of the equator. So, if a problem arises and they just have to come home immediately, they could be landing just about anywhere on the planet. That's problematic. This is an age before GPS and before cell phones. If the astronauts suddenly landed at some arbitrary point on the Earth, there would be no easy way to find out exactly where they were. You could look at their orbit and when they disappeared and get a pretty good idea, and the capsules do have radio beacons, but you'd still be talking about thousands of square miles to search. The Department of Defense kindly lent its assistance in the form of hundreds of ships and thousands of servicemen, but they couldn't be everywhere. For that reason, certain recovery zones were established. These were areas that the spacecraft would land in at the end of a successful mission, or where the astronauts would try to limp along to if there was a problem. If they could make it to one of these recovery zones, there would already be people waiting to help them. There were typically a few of these zones during ascent, since booster problems were so likely. There were also a few positioned so that if the astronauts arrived in space and something went wrong right away, they could immediately come home and land off the western coast of Africa. For the longer missions, the astronauts also had the option of landing at a few spots in the Pacific. And then, of course, the nominal landing site where they'd be expected to land if everything was a success. The crews were trained to survive in any kind of environment, so if they really needed to, they would initiate a deorbit burn right away and deal with whatever they encountered. But the hope was that they'd be able to keep things together long enough to use one of those dedicated emergency landing spots. Alright, while we were talking about that, poor Neil Armstrong and David Scott were stuck spinning faster and faster in their spacecraft. They had tried switching attitude control modes, tried turning off fuel and electricity for the attitude control thrusters, tried just about everything they could try. Finally, Armstrong tried one of the last options available to him. He pulled the circuit breaker on the entire OMS thruster system and turned on the re-entry thruster rings at the front of the capsule. Suddenly, the rates began to slow. It took a few minutes to completely null out the rotation, but the crisis was apparently over. So what happened? A short circuit in OMS thruster number 8 caused it to fire even when the control system had disengaged it. This particular thruster was used for both roll and yaw maneuvers, and with it firing full blast, it put the vehicle into an uncontrollable spin. It was only when Armstrong turned off all power to the entire OMS system that the thruster finally disengaged. Using the RCS rings at the front of the vehicle saved the day, but it came at a cost. These rings were dedicated to control during re-entry, and once they were used, they were committed to an emergency deorbit, the first in history. I think these guys would have been happy to leave this first to someone else and just stop at first docking in space. Since the immediate crisis was apparently under control, mission controllers and the astronauts decided to wait a few hours to land at one of the backup landing sites. This gave ground crews time to start rushing over to the recovery area and allowed the astronauts time to tidy up the cabin so things wouldn't fly all over the place during re-entry. After all, they'd already taken out stuff for the long mission. 4 hours after the emergency began, and only 10.5 hours after lifting off, Gemini VIII safely splashed down in the Pacific Ocean south of Japan. Armstrong and Scott were not able to complete many of the mission's objectives, most notably the extensive spacewalk. But that was okay. They were the first crew to be confronted with a true emergency in space. They stayed calm, they stayed professional, and they stayed alive. Being able to respond with a calm and rational mind to an unfolding emergency is a critical skill of all astronauts, and the response of this crew likely played a role in both of them going on to command Apollo flights in the years to come. In a way, successfully dealing with an emergency was an unspoken objective of Project Gemini. The whole point was to prepare for the monumental challenges ahead in Apollo. The more that Gemini could scout the path ahead, the easier these challenges would be. By discovering and dealing with an unexpected failure mode, Gemini VIII did just that. And Gemini VIII wasn't even quite done yet. Thanks to Armstrong's thoughtful actions switching Agena control back to the ground, the Agena side of the mission was able to continue well past Armstrong and Scott's splashdown. Crews on the ground used the main propulsion system to raise the vehicle to a higher orbit. Believe it or not, this is not the last we've seen of this particular Agena. But that will have to wait. Next time, we'll learn about the tragedies, the trials, and the angry alligators of Gemini 9A. Ad Astra, catch you on the next pass.